In this last video for chapter 2, let's take a look at how to solve two new types of differential equations. If a differential equation is not separable and is not linear and is not exact, turns out there are two other types, actually at least two other types. We're going to look at two more in this section. So let's take a look at this differential equation, which is neither exact, linear, or separable. So if we take partial m partial y, we get x plus 2y, and if we take partial m partial x, we get minus 2x. So clearly it's not exact. Let's rewrite it to see if we could notice it as linear. So if we first bring the x squared dy over to the right side and then divide through by dx and divide through by x squared, we get this, but since the y is squared, right here, it's not going to be linear. So let's take that left-hand side and reduce terms. And let's let y over x equal a new variable v. Then that makes the left-hand side v plus v squared. And then let's take this v equals y over x, and let's find out what from there, from that, dy over dx is. So if v is y over x, y equals vx, and if we differentiate both sides, we get on the left side dy dx, and on the right side by the product rule, v times the derivative of x is just v, and then x times the derivative of v is dv dx. So let's replace dy dx with this v plus x dv dx. And so then let's put that together into our new equation in the variables v and x. Before we go to solve that, let's just generalize that we were first able to take our differential equation and solve it for dy dx. The right-hand side, f of xy, we were able to write as a function of y over x. It could have been as a function of x over y, but since it was this case right here, we let v equal y over x, and then we solved that for y and differentiated and got this alternate version of dy dx. So we wind up with the alternate form of dy dx, which was v plus x dv dx, and on the left hand side we had, you'll recall, v plus v squared. So we're able to cancel out the v on the left and the right side, and that gives us a separable equation where we're going to put v on the left side and x on the right side. So let's set it up that way. So first we separate the variables, or we cancel the v, and then we separate the variables. And then we're going to integrate both sides of the differential equation, and when we integrate the left side we get minus 1 over v, and when we integrate the left side we get ln of absolute x, and then we're going to replace v with y over x. So we've replaced the v with y over x, and then the left side is not going to be any different, still ln absolute value of x plus c. And if we simplify that left side, it becomes what? Minus x over y equals ln absolute value of x plus c, which if we wanted to, we could solve for y, but it's okay to just leave it in this implicit form. So there's one homogeneous DE solved. Let's take a look at one more. So in this differential equation, it should be pretty clear that it's not going to be linear and it's not going to be separable because of how the x's and the t's are bound up differently. Let's notice that in the previous one, we let v equal y over x. We said we could let v equal x over y. In this case, it should make sense that we're going to let v equal x over t. And the way we see to get that is to use a technique where we just take a look at any one term in the expression we have and see what we need to divide it through by, or multiply it through by, so that it becomes a function of x over t. And doesn't it make sense that if we divided that term by t squared, it would work? Same thing would work over here, right? That would make that a function of x over t, and it turns out to work for all terms. So we are going to multiply the numerator and the denominator by 1 over t squared. And so where does that get us when we bring that 1 over t squared through? So we get dx over dt equals x, we get equals this. So we've divided everything through by t squared, and does it allow us to separate everything into the x over t form? Well, let's just take a little closer look at what we did here. First, let's just simplify it to v equals x over t, and then note here we divided through by t squared, and in the second term in the numerator, instead of dividing the whole thing through by t squared, we separated into a t, dividing by t out front of the radical, and then dividing by t under the radical. But since it was under the radical, it's dividing by 1 over square root of t, and then we divide it by t squared in the bottom also. And so simplifying this, let's see what we get. So this term right here, we are writing as x over t quantity squared. This term right here is just a 1, so we don't need to write since it's multiplying. This t squared over t squared under the radical is just 1 under the radical here, and this x squared over t squared on the radical is just x over t quantity squared under the radical here. And then finally, in the denominator, just becomes x over t. So let's make note of what everything is on the right-hand side in terms of v. So the x over t quantity squared is v squared. The denominator is v, and underneath the radical is 1 plus v squared. And so let's set up our differential equation. So let's first go through and calculate dx dt like we did before with dy dt. So x equals vt. We take the derivative of both sides, get dx dt on the left, use the product rule on the right. So we get v times the derivative of 1, which is just v, and then t times the derivative of v, which is dv dt. So that's going to be our left-hand side of the differential equation. So here's where we left off. Let's split the right-hand side into two fractions, v squared over v plus square root of 1 plus v squared over v. Notice that on the left and right side, of course we can do that kind of splitting because the right-hand side is a plus b over c, which is a over c plus b over c. And then we notice that we've got a v canceling on both sides because we have v on the left side and v squared over v on the right side. What remains is separable. We're going to be able to put the v on the left-hand side and the t on the right-hand side. So we're going to divide through by this and multiply by dt over t to get this. Now, to do the integral of the left-hand side, we're going to let u equal 1 plus v squared. That gives us du is, or du over 2 is v dv, so let's identify v dv as du over 2, and that allows us to set up the integral on the left-hand side as u to the 1/2 du. We can just go ahead and integrate the right side and get ln t plus c, and then let's integrate that left-hand side so we get the constant 1/2 is still there. U to the minus 1/2 integrates to 2, u to the positive 1/2, and now we can start, now we have the solution, we just have to switch back to the original variable. So we've got over here on the left-hand side just u to the 1/2, which is the square root of u, and on the right side we have ln absolute t plus c, square root of u, because u we let equal 1 plus v squared, so that gives us square root of 1 plus v squared equals ln absolute t plus c, and then the final step is to write that as 1 plus actually this is 1 plus v squared here, and v was what, was x over t, excuse me, right here, and so that is square root of 1 plus x over t quantity squared equals ln t plus c. So here is our solution in terms of the original variables x and t. So there are two examples of homogeneous differential equations. Obviously the second example is a little bit more complicated, but they wouldn't get any more complicated than this second example. So let's go on now to another type of differential equation, the Bernoulli differential equation. And so let's take a look at that on the next blackboard. So a Bernoulli differential equation looks very much like a linear differential equation. Up until there, it is a linear, or has the same structure as a linear differential equation. The difference is that q of x on the right-hand side is multiplied by a y to the n. When we have this type of differential equation, it turns out that if we make this substitution, we can change it into a linear differential equation. So let's see what that substitution is. It is to let v equal y to the 1 minus n. So let's see how, where n is that power on the y on the right-hand side. So let's, so we let v equal y to the 1 minus n. In this case, we're going to let v equal y to the 1 minus 3, which is y to the minus 2. And so we're going to, from there, find dv dx in terms of dy dx. So we differentiate the left side and get dv dx. We differentiate y to the minus 2 and get minus y to the minus 3 dy dx, because when we differentiate this right-hand side, we've got an outside function minus 2, and we've got an inside function y, so we use the chain rule. This part right here is the derivative of the outer function, and the chain rule says multiply by the derivative of the inner function. Now we want to take that and solve it for dy dx, so we're going to multiply both sides by minus 2y to the minus 3, and that gives us what, minus 1/2 y cubed dv dx. So we're going to take our dy dx and turn it into that, minus 1/2 y cubed dv dx, minus 5y equals minus 5 halves x times y cubed. And let's make note that yes, there is a y cubed appearing as a coefficient of the dv dx, and it is the y to the n on the right side. That's not a coincidence. When we do this setup right here to let v equal y to the 1 minus n, that will always happen. And so to clean this differential equation up, we are going to divide through by that coefficient of dv dx, which is minus 1 half y cubed, which simplifies the differential equation a great deal. It just gives us the first term on the left side of dv dx. The second term on the left side is what? Plus 10y to the minus 2, and then the what remains on the right hand side is 5x. So it looks like we may be in a jam because we've got this third variable y to the minus 2 in this term, and we want to convert everything to the variables v and x, but remember that we had let v equal y to the minus 2, and so if we rewrite the differential equation with that substituted in, we've got what? dv dx plus 10, and then the y to the minus 2 is just v, and that equals 5x. So it's now a differential equation, a linear differential equation in the variables v and x. And so let's take a look at how to solve that on the next blackboard. So here is the differential equation rewritten. The q of x is the 5x. The p of x is 10. So the integrating factor mu of x is e to the integral of 10 dx, which is just e to the 10x. And so this differential equation is solved for v, this linear differential equation is solved for v. So it's 1 over mu of x, which is e to the minus 10x, and then it is the integral of mu of x q of x, which is 5x e to the 10x dx, mu of x q of x dx plus c. Well, it turns out that this integral that we have to do is a somewhat complicated one, a parts integral. So let's go to the next blackboard to do that and then come back to this point. So we've got this parts integral to do. We're going to let, as in this type, u be the polynomial part, dv is the integral, or is the exponential part, exponential or trig, that's exponential in this case, du is dx, and dv, remember, is e to the ax over a, so it's e to the 10x over 10. The parts formula is uv minus the integral of v du, and so we have x e to the 10x over 10 minus v du would be minus 1/10 e to the 10x, or integral of e to the 10x dx. The parts method could succeeded because we're able to do that integral, so we get x e to the 10x over 10, repeating, and then integrating e to the 10x, we get e to the 10x over 10 multiplied by 1/10, so it's e to the 10x over 100 that we get. And so let's plug that back in where we left off. So we put the x e to the minus, or so we put the the x e to the 10x over 10 minus e to the 10x over 100 back in here. So we've distributed the 5 across. There should be a minus sign here. So here's the x e to the 10x over 10, and here's the e to the 10x over 100. We distribute everything across. We distribute distribute this e to the minus 10x across. What do we get? We just get what, e to the minus 10x times e to the 10x is just e to the 0, so that's just 5x over 10, or x over 2. And then the e to the minus 10x times the e to the 10x here just gives us the constant minus 5 over 100, which is minus 1 over 20. And then we have c times e to the minus 10x. And that is our v. But remember that v was equal to y to the minus 2, right? Or v was y to the minus 2, and so let's make this equal to y to the minus 2, and then call that our answer. That we could solve for y if we want to flip both sides. So let's actually write it in the solve. Leave it. Here is the implicit form, and then the solve for y form we'll write on the next blackboard. So we've got this. We're going to multiply both sides by y squared and divide by this x over 2 minus 1/20 plus c e to the minus 10x. I skipped a step here. And then when we take the square root of both sides, the square root goes here, and this side right here, square root of y squared, just turns into y. Let's do one final Bernoulli type problem, and then that will be the end of this video on section 2.6. So here we have another Bernoulli. The y to the n has a negative n on it. We let v equal y to the 1 minus n, which is 1 minus minus 2, or v equals y cubed. And we differentiate both sides. Dv dx equals 3y squared dy dx by the chain rule. Solve that for dy dx, and we get 1/3 y to the minus 2 dv dx equals dy dx. So we replace dy dx with 1/3 y to the minus 2 dv dx, and we notice again that y to the minus, or y to the n, appears on both sides where it was originally, and as a coefficient of dv dx. We're going to divide through by the coefficient of dv dx, which is all of this, or 1/3 y to the minus 2, and when we do that, we just get dv dx, first term on the left side. The next term, when we divide through by 1/3 y to the minus 2, so we're dividing the y by y to the minus 2, that gives us y cubed, and then the 1 over 3 gives us, divided by 1/3 gives us a 3 there. So the v was y cubed, and it's showing up in on the left side as in the second term. So this left-hand side can be rewritten as dv dx plus 3v equals e to the x, which is linear in v and x with an integrating factor mu of x equal e to the integral of 3x dx, because the p of x is 3, and so that gives the integrating factor of e to the 3x. The q of x is the right-hand side, e to the x. So if we put everything in place, here's the 1 over mu of x, and here's the q of x, and here's the mu of x, and then we are integrating e to the 4x. So continuing, we get what? E to the minus 3x. We integrate, we're integrating e to the 3x times e to the x, which is e to the 4x. And the integral of e to the 4x is e to the 4x over 4. We're distributing that across, we're distributing the e to the minus 3x across the c to get c e to the minus 3x. And then we're just, we're calling that v, but v, well, first let's clean it up. So v is e to the x over 4 plus c e to the minus 3x. v is y cubed, and we can then solve that for y as y equals the cubed root of the right-hand side, and there we have the solution to this Bernoulli DE. So we've done a couple of examples of how to solve homogeneous differential equations with substituting v for y over x, or x over t, or it could be x over y. And when we do the homogeneous type DEs, they turn into separable DEs. Then we did Bernoulli DEs, where we use the substitution v equals y to the 1 minus n. And when we do that substitution, these DEs turn into linear DEs, and they are relatively easy to solve, although we had one example where we had to do a parts integral in finishing out the linear DE. So this will conclude the set of videos on Chapter 2, and except for possibly some additional examples that I might put in a separate video.